1.
So what does surface tension have to do with space-time, dark matter, or dark energy? Isn't space-time an empty container? It's not molecules. Well, in this presentation, I'm going to show you that space-time does in fact have surface tension, and that if we manipulate the equations in a certain way, it looks like dark matter and dark energy. Then we're going to use those equations to calculate the velocity profiles of 15 galaxies. A lot of people know surface tension from a glass of water. They know that the interface between gas and liquid creates a membrane-like surface. But what a lot of people don't know is that every material surface has surface tension. The surface between two immiscible liquids has surface tension. The surface between a solid and gas has surface tension. Even two gas phases, humid and not humid, create surface tension-like behavior in clouds. Even people in a crowd, when separated by a barrier, create a surface tension-like wave properties. Why? It doesn't have to do with molecules. Surface tension comes from the statistical thermodynamics. We all know that if you have an assembly of things, it seeks maximum entropy, like the clothes in your room eventually cover the entire floor. And we create a surface by this dashed line. We can call two states, one above the surface, S1, and a state S2 below the surface, S2. If we somehow make it inaccessible to be in S1, then the probability of S1 diminishes, the probability of S2 increases, and what we've done is there's a decrease in multiplicity, which is also a decrease in entropy. In other words, we've organized the system more. This requires work. Physical chemists call the work of formation of surface the negative surface energy. Now, you need to understand that surface energy is mechanically equivalent to surface tension. I'm going to use this little wireframe model to demonstrate. This model has three fixed sides and one movable side. Across it is stretched a membrane with some energy density we're going to call minus Greek letter kappa. If we slide or move the one movable side some distance dx, creating some additional surface area, the energy required to do this is just simply equal to the surface energy density times the change in area. We can rewrite that change in area to be length times distance dx. Well, we also know that work is force times length. dx drops out of both sides and you get force over length is the surface energy density. Force over length has units of surface tension. So we see that surface energy density and surface tension are mechanically equivalent. This is known by all physical chemists. So why do I think space-time has surface tension? I'm going to give you a ruler and ask you to plot the location of everything in your room. In 3 coordinates of space, we have up, down, in, out, left to right. And it's going to look like a dispersed distribution like this, where you have things scattered around spatially in all directions. Now I'm going to give you a 4th coordinate, time. I'm going to give you a clock. And let's just ignore one of these spatial directions. Let's say up, down, and we'll develop another space-time diagram where we have time moving up and we have space in both directions. And what your plot is going to look like of things in your room is this. See, we only have one clock. We have one time. Everything in our reference frame, in your reference frame, is all at an infinitesimally thin increment of time. And so your space-time diagram looks like this. It's a surface. In fact, our 4-dimensional view of space-time for every observer has a 3-volume and 3 surfaces of time with 2 spatial coordinates. And what's true for one observer is true for all observers. So I say that if space-time is a surface in time for every observer, then we can look at a little element of that space-time and blow it up, and what you're going to see is that it not only has a distribution of mass, dp, which is normal to time, but it also has tension on all 4 spatial directions. Of course, this is just one of the 3 surfaces. So that means that the stress energy tensor doesn't just have a mass term, but it has 3 negative terms on the spatial diagonal, indicating surface tension. So, as you can see, space-time, although it doesn't contain any material, statistically, because things are organized in time for you, it has surface tension. The fact that we're not being bombarded by particles from the future or hit in the back by particles from the past means we have surface tension. Things are organized in our present for every observer, and what's true for one observer is true for all observers. So, we can do some little mathematical trick to manipulate this tensor. You can always subtract and add something without changing the tensor. So what I've done is add surface tension to this time term and subtracted it. But now you see we have negative terms along the entire diagonal. So we can rewrite this tensor as a mass term plus some extra term we'll call dark matter. And then we also have the octahedral stress times the metric, which we call the cosmological constant or dark energy. So you see how surface tension can be broken into dark matter and dark energy? Well, when we redo Newton's theory as a first approximation, we get gravitational acceleration is equal to, this is basically Newton's gravity, plus this extra term, which is frame independent and non-dimensional. Crazy. We can also write the velocity of stars going around a galaxy equals the sine of the inclination angle times, this is Newton's gravity again, and this is the extra term, which is non-dimensional, comes from surface tension. So what I did to see if any of this makes sense is plug it in for 15 different galaxies. I tried to pick galaxies that were a range of inclination angles, a range of distances from Earth, a range of size to get the maximum distribution of galaxies. I included some dwarf galaxies and some super large galaxies. And when you go ahead and plug in surface tension equations into these galaxies, you have to have surface brightness. Surface brightness is what astronomers measure is the amount of light coming from the center of a galaxy going out to the ends of the galaxy. R is measured in arc seconds because we have to have mass in order to plug into these equations. So the idea is we assume that the stars in these galaxies are like our sun. They produce a certain amount of light per pound. We call that the light to mass ratio. So if they produce the same light as our sun, we can estimate mass from these surface brightness curves, okay? And if we do that, we get this. And a mass to light ratio of 1, indicating all the suns in this galaxy are like ours, or on average they produce the same amount of light per pound. We get this curve here shown as a dashed line as Newton's gravity. The yellow dots represent actual astronomical measurement of rotation velocity. And so we all know that there's a mismatch, both in initial slope, so Newton predicts a much greater velocity initially, and then it falls off at 1 over r, whereas our astronomical measurements are flat. By the way, surface tension is way up above this, 10 to 20 times the velocity measured here, but that's at a mass to light ratio of 1. So I said, what if all the stars in these galaxies aren't like our sun? We know that in astronomy there's a whole main sequence of stars with different mass to light ratios. What if these are higher temperature stars? Then they'll have a different mass to light ratio. And by adjusting the mass to light ratio down to 0.42, I get the surface tension model to match the data. And I did this for all 15 galaxies. And we get a mass to light ratio of 0.41 and so on and so forth. So each galaxy, I just changed the mass to light ratio and you see how the model fits. By the way, changing the mass to light ratio doesn't change the shape. The shape comes from the equations. It just changes its magnitude. And so as you can see, the shape fits the data quite nicely when you include surface tension. Mainly, I just like looking at galaxies. So for reasons that will become apparent in the next slide, I plotted the relative mass to light ratio versus the square root of total solar luminosity. And you get this really nice inverse function. In fact, it has an r squared of 0.96, which is a really good fit. The reason why I did this is when you plug this back into the model, you get the velocity at extreme distances from galaxies is directly proportionate to the total luminosity of the 1/4 power. This is the Tully-Fisher relation. In conclusion, surface tension is just stress energy tensor with negative terms in the spatial diagonal. The negative terms can be rearranged to look like dark matter and dark energy. The additional dark energy term is too small to affect solar systems, but would govern galaxy rotation curves. Orbital velocities generated by the model compare well with measurements provided mass to light ratios are low. And best fit, galaxy mass is proportionate to luminosity and the Tully-Fisher relation. So if you'd like to read more about what I've done, I've published 3 papers in the Journal of Physics Conferences. You can download them at my website, copperresearch.com. And if you come to New York, I'm passing out these copper pins. We'll see you there.